Right, welcome back everyone. So let's start with today's lecture. Before that, any questions that you guys may have about the assignment, which is due on Thursday? We will still have the office hours tomorrow, 2 p.m. But do let us know if you guys have any questions. Keep an eye on the chat. It looks like we don't have any questions. So again, if you have any questions, just let us know. Oh, let me see. Sorry, I'm having troubles with my. Oh, Friday. You're right, Rob. Sorry about that. Yes, we changed the due date. Yes. So that's absolutely right, Rob. Thank you for pointing that out. Will you guys see my slides? Looks like someone is doing some of these crazy things.
Yes.
Okay, perfect. Thank you, Veran. Thank you, Rob. So we are going to be talking about linear algebra today, but linear algebra in is a slightly different way. Sorry, I'm having some echo. Yes, I have a question. The read module in the given code did not return any value, and the data were read into a temporary variable defined in the function. How should I test the module? Wow, that's a good question, Shishe. So it looks like your module is not quite modular after all. Let me think about maybe. So that's the reading module, right? Yeah, if you write to the screen, then you can redirect things. It has to do something with the data that is being read, right? If it is not being returned and you dump it to the screen, you can redirect into a file and then do a diff. That will be one way. A temporary variable, but how is that variable accessed? If it is just a reading module and then it doesn't return that variable, that data is kind of lost, right? Maybe because I think this is a particularity with the code, if you have time, maybe we can talk a little bit about that after the lecture. Do you think that will be okay with you? Okay, let's because I think it's something peculiar about the code that you got. So okay, perfect. Thank you so much. So as I was saying, we are going to be talking about linear algebra today, but in a different or a slightly different approach than the one that we usually learn in different courses in the university. We are going to be talking about how to tackle linear algebra numerically. For doing that, we are going to talk about a couple of packages or libraries, in particular BLAS and Apac, although there are many other ones, and we're going to mention a few of them. As a side note, we used to have 2 lectures on linear algebra. One was more on a theoretical side and a review, because linear algebra nowadays is so important and it shows up in so many different places. You may have recalled last week our PDE lecture, where at the end we ended up doing just a matrix vector multiplication for evolving the partial differential equations, for solving the partial differential equations. But on top of that, we have linear systems, we have properties of the system such as stability, direct solvers, iterative solvers, a whole set of different applications that linear algebra offers in many different fields. So it's a really cool area of research, but also of implementing solutions numerically. And of course, we had a dense versus a sparse matrix approach, something that came up also last class. So we used to have this theoretical review. It was a whole lecture. For the sake of accommodating more material on the practical side, we removed that, but we do have some links to the previous lectures where we discussed this. But again, bear in mind that this is very desirable to have at least some of these concepts fresh in your mind. So if something is not quite clear or some jargon is not, you're not familiar with, just let us know. We try to clarify as much as possible. Now, so how to write numerical linear algebra? Well, as much as possible, rely on existing libraries. There are plenty of libraries quite mature that have been around for a while, and they are not only, you know, optimized for taking the best advantage of the computations, but also they have been developed for many people and many years. So it's quite possible that, or they are very reliable. That's what I'm trying to say. This will allow us to focus on the code, on the detail of the codes that we're trying to implement, to reduce the amount of code to produce and debug, of course. And as I say, libraries are tuned and optimized, so your code will run faster. And there are also more options to change the methods that you will want to try and experiment. So let me go through a few of the resources that are in terms of linear algebra. So one that is quite reliable is called Netlib. So this is maintained by, I think it's University of Tennessee and one of the national labs in the States. Most of the code is public domain or freely licensed, so you are more than welcome to use it. The thing that could be quite surprising is that it's written in Fortran 77, which is, you know, if you just hear the word Fortran, it will ring some bells, but Fortran 77 is like the very old version of Fortran. Having said that, it has been there for a while, has been around for a while, and then it made them quite reliable, and people still use it, and they perform quite well, I would say. In particular, this is the source for BLAS and LAPAC. BLAS stands for Basic Linear Algebra, and LAPAC is Linear Algebra Package. And we're going to see examples how to use them today. So, but bear in mind, similar to what happened with NestEDF, that there are different APIs, these routines have been written in Fortran, and we will need to do some manipulations how to pass the data into these libraries. One which has a way modern approach, although a little bit more convoluted to use, is PHY. This is maintained by Argonne National Labs, another of the national labs in the States. It's open source, and it's primarily, if not all, C++ code. The thing with PHY is that it's well used for partial differential equations and iterative linear solvers. So it's not just basic linear algebra. Indeed, it may use some of the BLAS and LAPAC subroutines at the core, but it's mostly C++ routines. And then there is another one from the national labs in the States. They are quite busy doing linear algebra, called Trilinos. This is maintained by the Sandia National Lab in the States. It's a collection of 50 plus, probably more now, packages, includes linear solvers, preconditioners, and many others. So it's a good resource to keep in mind when you're looking for a particular algorithm or method to implement in the linear algebra domain, let's say. Okay, and all of them are open source, so that's the neat part, and they accept contributions from the community. So it's kind of there's sanity checks in place for this library. So and they are well known and they are robust. So it's a good place to look at potential solutions for methods or implementations you may want to try. And there are others, of course, but these are the main ones I would say people usually use. So let's start by looking at BLAS, which, as I say, stands for Basic Linear Algebra Subroutines. It's a well-defined standard interface for routines. They have many highly tuned. Yeah, there is NumPy. But you know what, Gabe? Funny thing is NumPy, when you start, this is a very interesting fact indeed. When you install Python, and in particular NumPy or SciPy, and you have LAPAC or BLAS installed in your systems, you can hook, actually NumPy will hook the routines, the basic of the routines to these libraries. So at the end of the day, we can start a whole discussion about performance with Python and things like that. Ramsey has an excellent lecture. It's kind of a workshop style thing where he analyzed performance of Python code, high performance Python. And sometimes things are surprising. But one of the surprises that you may find is that, in particular, if you use in our clusters, the NumPy subroutines, they are compiled, linked to, or linked versus these libraries. So it's not, I don't want to start a whole discussion on that topic, but yeah, so NumPy will do the equivalent for you in Python. So one thing that is interesting and it will show up in our examples is that the interface and implementation are different, and basically you need to understand a little bit of the jargon, and we're going to see that. Includes higher order operations like matrix factorizations and Gaussian elimination, which are defined on Apac, which relies on top of BLAS. So there are Apac you can see as a higher abstraction layer on top of BLAS, and BLAS implemented the very basic routine. So they are kind of intertwining in that regard. This is a little bit of the nomenclature in BLAS. So BLAS, and the same will happen on Apac. So they follow this sort of convention. They have 3 levels of routine. Level 1 for basic routines, let's say. So this includes things like dot products and A being a scalar times a vector plus a vector. So routines that they deal basically with vectors are what we call level 1. And the routine, for instance, here is S dot for scalar dot or scalar product. The S stands for single in this case. So the first letter corresponds, is what we call the prefix, corresponds to what is the type of the data that we are using. In set corresponds to a double complex. So in this case, A is a scalar times a vector plus a vector will return a vector, which in this case is going to be a complex vector. The level 2 routines are matrix vector multiplications. So anything that can be implemented using matrix and vectors, the type of operations that involve matrix and vectors are what we call level 2. Same convention applies. The first letter, the prefix, corresponds to the type of the object that we are going to return. So D is for double, and G is for general, and so what it means is it's a general matrix times a vector. D here is again double the type, but sim corresponds to be a symmetric matrix times a vector. So general matrix times a vector, symmetric matrix times a vector. By selecting the name, by selecting this way of encoding the information, we can also give information about the structure of the matrices, and these routines take advantage of that. So if you know that you are dealing with a matrix that is symmetric, then you better use the routine that takes advantage of the structure of the matrix. And these are the type of metrics that BLAS supports. G is for general, HY is for Hermitian, SY is for symmetric, TR is for triangular, GB is general banded, HB Hermitian banded, SB symmetric banded, TB is triangular banded, and TP is triangular packet. So different ways to encode your information on the matrices structures again. And finally, level 3 is when you have matrix-matrix operations. So S again is for single, GEM is general matrix, and this is a general matrix multiplication. C in this case is for complex, and TRM will be a triangular matrix times a matrix. Somehow the names are cryptic, but I think after using them a little bit, you get used to this sort of convention. Okay. If you go back to our example from last class, the PDE, you will see the weird name like cBLAS underscore something that was calling one of these functions. Okay, and again, the cBLAS thing is the C interface to these Fortran routines. That's where the cBLAS underscore thing came from. Now, the question you may wonder at this point, just thinking about the very basic of, take the level 3 example, where we multiply two matrices, is why should we bother, right? You need to find the right package, the right library, perform the installation, figure out how to link, which, as you may have seen by now, is not trivial. There are C and Fortran issues that we are going to talk about. And why just not write a matrix multiplication routine? After all, we are talking, if it is a two-dimensional matrix, we are talking about 3 nested loops, or n+1 nested loops being n the dimension of the matrix. So why not just doing that? I mean, it's quite straightforward, sort of. Well, this is one of the reasons. I will argue that, as we mentioned several times on the course, no writing code is one of the best ways to avoid having bugs. So by writing more lines of code, you increase substantially the chance of including bugs in your code. And debugging is something that we try not to do as much as possible. So the other reason is performance. So this plot shows the number of operations, or the performance in gigaflops per second. So gigaflops is a way to measure floating point operations, meaning operations, computations that the computer is doing per second. So it's a matrix multiplication test case on 2x2 cores at 3 gigahertz. It's just a standard, just a baseline for computing this. Probably it's old now, but it's just that. So you can see the number of floating point operations per second. And what I would like to mention here is the triple loop is at the very bottom of this plot. Okay, this is a linear plot, not log plot, nor anything like that. But the triple loop that we just saw before, the straightforward implementation that one could think of, lies at the very bottom of this plot. And this, of course, depends on, you can see with the matrix size, is almost flat. But as you can see, including or using other approaches like best scalar code or best vector code or threads, improve the number improve the performance substantially, almost by a factor of 9 or 10 in some cases. And this basically comes for free whenever you use one of these libraries, because many of these libraries has threading implementation on them already. Just a word of warning: sometimes you need to switch this threading thing. We haven't talked about threading yet. We're going to be talking about that in a few weeks when we start the parallel part of the course. But basically, it's using one of the processors and multiple instances of the process running within, and taking advantage of the capabilities of the processor of performing multiple operations simultaneously. So as you can see, by using these routines, not only you gain in the fact that you don't need to write code, you reduce the fact of introducing bugs. You have routines that have been optimized for performing well, but also you have routines that have been optimized to take advantage of the structure of the matrices, which is quite important and relevant in the moment of computing things numerically with matrices and vectors. So this is kind of a justification slide, if you wish, why you will do that. So we talk a little bit about the basic BLAST routines. Let's talk a little bit about the interfaces. So the netlib website I mentioned at the beginning provides a reference for the implementations, both for BLAST and LAPAC. So that's your main source of reference. And as you have seen with these libraries like netcdf or Boost or GSL, you will have to read the documentation. That's part of the deal. And that's where you will go for the documentation, the netlib website. Now, one thing to bear in mind, and this is because we will be using these libraries on the cluster, although BLAST, the open BLAST version of it is very easy to install. It's probably one of the easiest libraries to install. Most of the vendors of the hardware vendors provide optimized version of this, because these are open source products. They can take it and optimize, tweak a little thing, some things to take advantage of the actual architecture of the hardware they have, and optimize things a little bit. So for instance, Intel has its own MKL, which stands for Math Kernel Library, and AMD has ACML, and IBM has ESSL. So each of them provides its own library for linear algebra, and as I say, they are optimized for the hardware they are selling you, right? So if you, in other words, if you are compiling your code or running your code in a system that is Intel, then probably you want to try MKL, similar if you are using AMD or IBM. So the open source alternatives to that is to use ACLAS, that's another set of libraries, GoToBlast or OpenBlast. OpenBlast is the one that is almost guaranteed to work anywhere, from macOS to Linux. Haven't tried Windows though, but anything Nix compatible, I would say it should work. As I mentioned before, these are Fortran functions, so the implementations are done on Fortran, but there is a C interface for CBLAS and LAPAC-E. So notice the difference here. BLAS and LAPAC are the original implementations in Fortran. If you want to use the C interface, you will be using the CBLAS and LAPAC-E libraries. Okay. So how to install BLAS? And as I said, this is almost trivial to do with OpenBlast. You will go to openblast.net, and then there's a Git repository that you can clone, use CD into OpenBlast. You need to specify which Fortran compiler you want to use. We have been using the new compilers, and as there is GCC or C++, there is also a C-Fortran compiler within the new compiler. So you will set FC, the variable FC for Fortran compiler, to use C-Fortran. Then you do make, and that will compile the library. And then you do make install, and then prefix says, where do you want to install the OpenBlast library? As I say, it's quite straightforward. This is an example, just an example of how you will do it. For let's say, for using these libraries in a frequent manner, one thing you can do is include in your bashrc, your file bashrc, which is loaded every time that you start a new shell, the blast inc and blast lib variables, and that will point to the OpenBlast directory where the library was installed for the header files and for the library itself, and then add that to the LD library path, which is the dynamical linking directory for libraries, and that will do it. Basically, that's all what you had to do. So again, it's usually that I haven't seen people struggling with this type of installations. So it's something that is quite trivial. I can remember now, I think we have BLAS installed in the cluster, but I think we usually ask for I think it's going to be next assignment to do your own installation. We will see that. I can't really remember now. Maybe Francis can recall about that. I'm sure this was something we used to ask our students to install in your local computer, because as I say, it's one of the almost straightforward guarantee to work 99% of the time. So you may want to give a try. So if you're going to use the Niagara cluster, there is a module, probably this is an old one now, but there is an OpenBlast module that you are welcome to use. As I say, I can't remember, but you are welcome to spider on the Teach cluster to see if we have OpenBlast installed. Probably we do have, but we still may ask you to do your own installation for the assignment. We will see. So Alice is asking, can we keep the LD library path as is or replace the directory in our sign account? You can keep it as it is. So notice that this line here is not overwriting your LD library path, and that's why the order matters. So when I'm reassigning LD library path, the first thing I do is to do $LD library path. So what I'm doing here is appending to whatever was on the LD library path the new path of the library where I installed. That's basically the whole trick that the module system does. It appends things to your environment variables, and then you add to them. Oh, great, Ramses, thank you. So that was my recollection. Yeah, we don't have OpenBlast on the Teach cluster, and if I remember correctly, this was on purpose, because on the next assignment, which will be something about linear algebra, we usually ask you to do your own installation of OpenBlast. So yeah, you may want to keep in mind this slide, and usually, as I said, this should work pretty straightforward, in particular in the Teach cluster, which is a control environment for us. Okay. So let's take a look at, no problem, Alice. Let's take a look at a first example of BLAST routines. So we're going to start simple because these routines, in addition to the jargon they use for the naming and the conventions, they also use some ways of calling things or using things that is not quite, what you will expect. Let's say it that way. So the first thing that we're going to look at is the scalar product of a scalar times a vector. And this is represented by the D scale function. D is because it's going to be double, and then because it's the scalar product between a number and a vector. One of the things that you will see also is these routines are, I don't know if they were the right way to say is efficient, but they try to minimize the amount of variables that you will use. Let's put it that way. So what will happen is it will take a vector x, multiply by a scalar alpha, and return the result this into the same vector x. Okay. Why? There are some technical reasons for this, but also, as I say, some optimization that you can think of. The technical reason is, as we say, these are Fortran routines. So things has to be passed by reference into the Fortran world. So basically, the routine will operate on the vector that you are passing as an input, but also for returning the result. So let's take a quick look at how we are going to do this. So we're going to include IOStream for output things, and then we're going to include the CBLAST implementation of the BLAST library. We have a main function receiving arguments, and then I'm going to define a vector with 3 elements, 1, 2, and 3, a coefficient that will be over alpha, and then we need a couple more of things to be defined. So this one is going to be a pivoting thing that we're going to see what is the usage later. Basically, it's a stride. So these functions can operate every certain number of elements. So I want to operate on all of them. So I do the stride to be 1. And then the other thing that we need to specify is the dimension of the vector. So we have 3 elements. So by doing dscal_, we are calling directly the Fortran function. And that's why we need to pass the things with this ampersand just for referencing to the memory location of these objects. The first thing that we are going to pass into the function is the number of elements. The second is the coefficient that we're going to multiply, what I call alpha here. The third one is the pointer to the first element of the vector. And the third one is the stride, as I was saying, how many elements you want this function to operate. Do you want to operate with 2 elements, every 3, whatever. That's the call. That's all what you had to do to multiply the coefficient by each of the elements of the vector x by the coefficient. And then you just print out the result. Nothing much to that. Just an example of how you invoke this function. This is the counterpart using the CBLAST interface. So most of the code is the same. Notice the things that change, though, are in this line below the comment. So instead of doing dscal_, we do the CBLAST_dscal. And then all the arguments remain the same, but without without passing them as the reference, the memory pointer to the variable, just passing the variable itself because it's the BLAST interface. There are no real, as far as I can tell, advantage between one or the other. It's more of a commodity thing or how you feel more comfortable programming. So, pick your way of doing things and just stick to that. That's the only advice I could give you about this. Okay, but again, just one function call for performing this scalar vector multiplication, right? Other things that you may be interested in knowing is how are we going to compile this? Well, I call this file dscal.cc. So we roll French C++, standard 14, the output for the executable, and then how to link to the header and library. And one thing that we have seen, this you may recall from Ramsey's library lecture, we need to provide the name of the library. In this case, the library is called OpenBLAST. If you are compiling on Cynet, again, this is more than on Cynet or Niagara. You can use the OpenBLAST module, but not on the Teach cluster. how you will run it, you execute, and you get the product. So Michael is asking, is there a reason why they include both functions if they do the same thing? You mean both implementations, both interfaces, the C and the Fortran? I think it's because originally the routines were developed in Fortran, so they want to be kind of, straight to that, and also because the library can be used for Fortran or C. So I think it's more of a, you can think about this as being an API. So you can use it in Fortran, C, or C++. So that's I think why they try to make it usable for anyone. So yeah, but it's a good observation. Yeah, so this is another example. This is the matrix multiplication. This is provided, and we're going to consider that this is a general matrix, or general matrices, both of them. So the routine, that's the interesting part again. The routine, what uses is the following. Let's say that I had to multiply A times B. Well, the double general matrix multiplication routine does much more than that. It can provide, or it can perform the general operation that provides a scalar multiplying the vector of the matrices plus an offshift, a shift in another matrix. The interesting thing is that the second or third matrix that you are going to add is the one which will receive the result. So let's say, again, you want just to multiply two matrices. Well, the function you want to use, and this don't have any particular underlying structure, the function you want to use is the double general matrix function. And the function will implement the multiplication of A times B, being A and B matrices, times a scalar, a number, plus another number times a third matrix. So in general, the C matrix, you will put a 0, and then you will receive the result of A times B in that C matrix, for instance. One important thing is, as I say, there is the documentation on the netlib website, but also when you install the libraries, there is the man pages, and this is something that is quite common and quite useful, especially if you are in a Linux environment in the terminal. You don't need to be browsing the internet or anything. You can just do man and the name of one of these functions. And this is sort of the information that provides you. So it tells you what operations it performs. It tells you basically how it's defined the operation. So alpha times the operator A, operator B, plus beta times C. And then it tells you a little bit of which are the arguments. And you can see as the functions grow in complexity, the number of arguments also increase. So we will have a trans, which stands for the transpose of the matrix A and B, the dimensions of the matrices, the leading edge of the matrix. We're going to see that alpha, which is a scalar, the matrix A, then the leading dimension of the matrix A, the leading dimension of the matrix B, beta, which is the second scalar here, C, which is the third matrix, and the leading dimension of C. Okay. So a lot of elements. So let's take a look at one of these arguments, which is something that shows up very frequently in basically all the functions that involve a matrices. You will see something like the leading dimension of the matrix. So what it means is, perhaps, and this happens a lot with big matrices, or the special matrices has an underlying structure, where the example I always like to think about, and this is where your linear algebra remembrances may start to show up, is about the short and canonical form of matrices. So when you have one of the big deals in matrices or linear algebra is to diagonalize your matrices. If you diagonalize your matrices, that is really good, because many of these methods are optimized for diagonal matrices. Basically, you only need to operate with the diagonal because the rest of the matrix is zero. It turns out not all the matrices are diagonalizable. So if they are diagonalizable, then you need to find a particular basis where you change the representation of the matrix, and then you are in good shape, because basically it all turns out it's very simple to implement. But many matrices are not, or they don't have a closed diagonalizable form. but instead they have what we call a canonical shorthand form, which is basically a diagonal form by blocks. And that is a very neat generalizable idea of diagonalizable matrices. It turns out this has physical representations depending on the system that you are looking at. But bottom line is you may end up with these blocks. So let's say that you want to operate with the blocks, but not with the whole matrix. So you can specify that by saying, okay, instead, this is my whole matrix, all the information is encoded there. But what about if I just had a block within the matrix that I want to operate? So the leading dimension of the matrix allow you to select, okay, M in the routine that we were having before, the argument M will be the size of the block. And then the leading dimension is, okay, the distance between the beginning of the block to the next edge of the block. And think about this again. We saw this, I think, when we saw R arrays and multidimensional arrays. The way that this matrix is represented in memory is in a linear structure. So we have the rows, right? And we have the columns. Now, C is what we call a column major language, means that the columns are the ones that are laid down continuously on memory. So I have the first column, second column, n column, so 3, 2, 4, 2. That's the block that shows up continuously here. Let's say there is a block is dimension 2, so I have m equal 2. But then I have, excuse me, I have another set of values until the next part of my block. So 3, 3, 4, 3. That will be my next column. So the leading dimension here represents, okay, the distance between the edge of one block and the edge of the continuous part of the block. Okay, that's why the leading dimension is useful. In most of the cases, if you are not working in these patches or blocks within the matrices, the leading dimension is nothing else than just the dimension of the matrix. Okay. In addition to that, BLAS, because again, it's Fortran-based or Fortran-developed code, allow you to pick a row major or column major representation for your matrices. Okay. I see a question for Beran. Is this why the library has a higher performance compared to the nested loops? There are many reasons why the library has better performance. One of them is that it takes full advantage of the structure of the matrices by being able to specifically pick which function you want to use. I can't go into too many of the details because, first of all, I'm not quite familiar with the details, but I'm pretty sure engineers have spent tons of time, and computer science engineers have spent a lot of time analyzing what is going on with the performance at the very low level of these interfaces. So one of the things is, I would say a big chunk of the things is taking full advantage of the structure of the matrices, but also optimizing the way that these operations are performed. At some point, when you look at the algorithms of what they are doing underneath, you lost completely track of the actual problem, of the actual mathematical problem, and then you are just optimizing operations, right? So yeah, it's a little bit of everything, but the structure matters and matters a lot. So let's go back to our example of the matrix multiplication. This is probably one of the most general examples that you will see. So we started with one which is quite simple, but then let's take a look at this other one. So again, we're going to include the CBLAS library. And now we have to define a few more things, right? We need to define the three dimensions. So these are going to be a square matrices. So M, K, and N represents the dimensions for each of them. Of the matrices, then we will have two scalar quantities, which are the alpha and beta parameter that shows up in the definition of the function, and then we will have our three matrices, which are defined as basically a pointers and allocating space for them. Now, one thing that you may remember from matrices is the dimensions of the matrix for multiplication has to match. And this is why the representation of MKN, so you can have the freedom of changing those values, make rectangular matrices or something, but this way of defining the matrices will guarantee that by the end, you will end up with a n by n matrix, being n by n the product of a n by k times k by n matrix. So if you keep those notations, it will match independently of what dimensions you put in the matrices. What we're going to do is just initialize with some arbitrary values the matrices. As I say, the C matrix is going to be initialized with 0. I could leave it as it is. It's always a good idea to initialize them, though, because if you put the parameter beta to be 0, then this term won't contribute. But just for the kicks, let's put it as 0. A and B has just values, and they are turned into doubles by casting them into doubles, but it's just offsetting the index value +1 and -1, just again for the kick of doing some filling the values of our matrices. The call, and we're going to use the C call in this case, the call to the function is as follows. So we're going to do C blast double general matrix function. We have 3 labels. These are defined on the blast library. And we're going to say, okay, these are row major matrices. They are not transposed for each of the A and B. Okay, so A and B are not transposed. So then what follows is the leading dimensions or the dimensions. Sorry, these are the dimensions of the matrices M, N, and K. Alpha, which is 1 because we just want the product of A times B. A, the leading dimension of A, which is case I pick K because it's the whole matrix. B, the leading dimension of B, the parameter beta, C, and the leading dimension of C. And basically that performs the matrix multiplication A times B and put the result back on C. If you run, and of course I'm omitting the output of the matrix just for not putting the whole code here, but if you run the code, you will get the matrix A, which is a 5 by 5, the matrix B 5 by 5, and then the multiplication of the matrix. And again, it's just one call, right? All this preamble is just for defining the matrices. They are the way you will have to do it, but the matrix multiplication is just the call to the C blast routine. Okay, and as I said, this is one of the more generic cases or general cases that you will find in linear algebra in terms of basic operations of metric vectors multiplications. Any questions about this? We're going to be switching gears to Apac, which has some more interesting features based on this and more linear algebra methods. All right, so let's talk about Apac. Apac stands for Linear Algebra Package. Contains a variety of routines for solving linear systems, matrix decompositions, and factorizations. Internally, that's the substantial element here, uses BLAST calls. So all the basic operations that Apac will do or implement will be through BLAST. Supports the same data types, single, double precision. So the convention that you learn for the names for BLAST, they are going to be applicable here, like S set. All the things will represent the same thing. Similarly for the type of matrices. So you can still keep, and it's encouraged and recommended that you keep still taking advantage of the structure, the underlying structure of the matrices. Similarly to BLAST, it has 3 categories: auxiliary routines, computational routines, and driver routines. And we're going to see examples of this. There is, again, this is a Fortran C word, so there are C interfaces that are prefixed with Apac E. And the documentation, again, is through the netlib website. These computational routines are designed to perform single specific computational tasks. So they are very concrete, and this happens a lot in this type of implementations. For instance, it can perform factorizations like lower triangular, upper triangular, lower triangular and the transpose, or lower triangular Hermitian, and LDLT or LDLH, QR for orthogonal decomposition, LQ, QR set generalized for Hermitian matrices, and a bunch of many others. It handles symmetric Hermitian and non-symmetric eigenvalue decompositions. That is very interesting for many different fields. It also handles singular value decompositions and generalized eigenvalue and singular value decomposition. So if you are doing quantum mechanics or effective field theory or anything, those should be reimbursed for you, because they are something that's quite common and very, very frequently used. Similarly, as BLAS, it has man pages. So it was very similar. After you understand more or less the modus operandi of one, is very, it can be translated very easily into the other, at least how to get information. So we're going to see one function called DGSB. And so D again is for double, G is for general, and then SB is for solving a system. So it will solve a system or a linear system of the type AX equal B. So being basically over unknown X, and then A is the matrix defining the system, the linear system, and B is a constant vector. So DGSB, this is taken from the man page, computes the solution to a real system of linear equations, AX equal B. Now, one of the nice features, this is again, is something quite handy, especially when you are dealing with numerical issues, or numerical implementations, I should say, is that this function can solve many systems at the same time, governing by the matrix A. And the way to do that is actually the vector B can be the composition of multiple vectors B. Another way, you are solving for different independent or constant terms B. So the routine is called in this way. N is the dimension of the matrix. NRHS is the run height size. A is the matrix defining the system. Notice we still have leading dimensions here, so you can use this division of blocks or patches within your matrices. So we have a leading dimension in A, a leading dimension on B, because B, as I say, can be seen as a matrix composed by many multiple independent vectors. The info is a flag for returning if it was successful or not, the solution. And then we have IPIB, which is a pivoting index. So the method that it is going to use, this was part of our previous review, the method that is going to be used is some sort of Gaussian elimination. And for doing that, is going to be pivoting columns and rows in the matrix. So it provides you the information of how the elimination was performed. So basically, it does the solution by decomposing. It's telling you exactly this right here is decomposing the matrix A into a lower upper triangular form and a matrix for the permutation of the matrices. And basically, the IPIB has the information of this permutation of matrices. So an example of this, and as I say, this is where things start to make contact with the linear algebra knowledge that you may have. So if there is something that is not clear or you need to catch up with some of the concepts, just let us know. So we are going to include the Apac E library in this case. I'm going to just define a few constants as it's easy in that way. So we're going to have the size. Basically, this is how many elements we have in the matrix. We are going to have how many right-hand sides we have. So this is the number of B vectors I'm going to use. I'm going to use 2. The leading dimension of the matrix A is going to be equal to the dimension of the matrix. So I'm using the whole matrix, in other words. Similarly for B. B is again our vector of unknown, of constants, and it will have 3 entries. Okay. So how does it go? Well, I start by defining a matrix that will store the pivoting indices of the permutation. So it's something that the function will provide for me. And then the information flag is an integer indicating if the solution was achieved or not, how it was performed. I'm going to define my matrix a different way. Instead of allocating the memory, I'm just defining on the spot the matrix. It's a particular matrix with a given value. And then 2 sets of vectors B, one corresponding to the first line here and the other one to the second one, all of them defined continuously in memory. So they are all laid down as it were a matrix, as it were a vector of 6 elements, but actually this represents 2 independent vectors of 3 elements each. How we solve the system? Straightforward call to the Apac function. So it's Apac E underscore, because we're going to use the C interface. It's going to be a column major representation. That's what we are saying here. The dimension is n. It's a 3 by 3 matrix. Number of right-hand sides, because we have 2 vectors that are encoded in the vector B, is 2, given here. A is the matrix itself. The leading dimension of A is M because it's the whole matrix. This is where part of the information is going to be stored, IPIB. And then the information about the vector B and the leading dimension of B. Okay. How we compile this? Well, very similar as before. And we use basically the Open Blast interface and names for the libraries. And one thing is, because we are solving for 2 vectors, the solution of X will contain 2 solutions, will be 2 vectors, because we are solving 2 systems at once. Why the Apac implementation has this? Well, because actually by doing the decomposition of the matrix into the pivoting matrix, in the lower and upper triangular shapes, then you can do that. You can, after you perform the decomposition, you can solve for free, basically, as many systems as you want. That's the thing. When you look at the details of the composition, basically this is the LU factorization the algorithm reaches, and this is the pivoting index used for decomposing the matrix in such a way. So all that information can be recovered from the call to the function. Okay. Any questions about this? Okay. So I think someone was asking, I think it was Rob last class, I was asking, okay, what about non-dense matrices? Well, we have different types of non-dense matrices, or sparse matrices, if you wish, matrices that contains a lot of zeros. The really nice ones has some underlying structure, like banded. So this one, for instance, has the elements in the diagonal being non-null and the sub-diagonals being non-null neither. So this will be a 3-diagonal matrix, and this one you can access by doing the type, for instance, double, general, triangular, or banded, or symmetric positive. These are very nice matrices to work with, because you basically are guaranteed that you get positive eigenvalues for the whole matrix, and that allows the methods to perform nicely. So yes, structure again matters a lot. And if you have a hint, because you know the type of problem you're solving, and you know the type of structure that you are expecting that your matrix will have, try to take full advantage of that. That will help implementing the performance and also implementing the methods properly. Let me show you, because these matrices show up quite frequently. And you may, if you recall our last class, is the type of matrix that we actually have for solving partial differential equations, where a stencil of the representation of the evolutionary differential equation has the diagonal, upper and lower diagonal. But of course, this can increase depending on the orders that you include in your approximation for the final difference scheme. So a higher order final difference approach may have more sub-diagonals, but the structure is still banded for these matrices. So let's take a look at how we will deal with a matrix like this, with a diagonal and upper and lower sub-diagonals. So the nice thing is we don't need to store the whole matrix, and we can use a function that doesn't need the whole matrix for performing the operations that we need. So in this case, we're going to still solve the system, but we're going to use the double general 3 diagonals or banded, if you wish, and then the solution to the system. So same things to include. I'm going to, so in this case, it's a 5 by 5. So it's trying to represent this matrix, but as a 5 by 5 matrix. And we're going to just use for demonstration purposes. Actually, this is 3. This is a typo, sorry. This should be three independent vectors on the right-hand side. And the nice thing is, so the leading dimensions are still the same size as the matrices. So it's 5 by 5. So no changes there. But the interesting thing is we don't need to define the whole matrix now. I can define the lower diagonal, the upper diagonal. Notice these elements, because our sub-diagonal has 1 element less than the dimension of the matrix. So it's 144, 144, 1441, sorry. The diagonal, which has 5 elements, so the same size or dimension as the matrix, and these are all -2. And then the independent term on the right-hand side, which, as I say, should be 3, not 2. I apologize about that. And then 5 elements for each. Now we call the Apac double general tri-diagonal application or function, column major, as we were representing, dimensions, number of right-hand sides. And this is where it changes. Instead of passing the matrix, we pass the 3 diagonals or diagonals and subdiagonals. The lower diagonal, diagonal, and upper diagonal. The number of unknowns or constant vectors on the right-hand side and the leading dimension of that. And again, this has a lot of advantages in terms of memory imprints, like it will use way less memory than the full representation of the matrices, but also in terms of performance. No, that's right, Beran. We want to allocate the memory so that it lays down. So this is another of the technicalities. You want to have the memory lay down linearly in the memory. So you really need to be careful with that, I would say. It's a good observation. Compilation was as before, and then by running the code, you just get the 3 solutions for the 3 systems that we are solving at once. Okay. This is a nice example because it shows how to take full advantage of the structure of the matrices. Just a quick observation. I'm sorry, I don't have much to say. I know some of you may be working with Sparse matrices, but it has been, you know, people have been working on this field for quite a while. And as far as we know, we don't know any de facto standard for dealing with sparse matrices. But there are 3 potential options or 3 possible alternatives. There's a sparse blast, but I don't know if it is available. It's something that, again, it has been under development for a while. Then there is a nice sparse blast, an alternative blast system that you can try. And then there is the matrix template library, C++ library, provides support for some sparse matrices, but I don't know how extensive it is in terms of the implementations they have. It may have matured. Maybe, I haven't looked into this, but maybe Boost, we were discussing some time ago, Boost has grown exponentially in the amount of things it's achieving. So maybe even Boost has some support for sparse matrices right now. I can't really tell. These are some useful links with more examples and implementations of different linear algebra routines. So it's a good source of information. And basically the message that we want to convene for today is you will notice linear algebra popping up everywhere in every different implementation. Even if you go to machine learning, the methods underlying gradient descendant, all type of methods are supported, empowered by linear algebra methods. So they are basically everywhere. Partial differential equations, ODE solvers, signal processing. Fundamentally, if you know about the structure of your matrices, please use them. It will help the methods a lot. It will make them way more efficient and definitely more robust as well. Choose methods based on system properties. There is something called condition number. We haven't talked about that, but that's quite relevant, especially when you need to solve dynamical systems. Sparsity, if you have good routines for dealing with sparse matrices, there are not too many, as I say, but you may want to explore that. And there are many highly tuned packages for any sort of problem that can be cast into matrices. The ones we saw today were Apac and BLAST. But as I say, Trilinus and PETSI are good alternatives as well, especially if you are more inclined to deal with C++ annoyances and not so much this C/Fortran word or implementation of that. There was something else that I wanted to mention, but now it's escaping my mind right now. But I'm happy to answer any questions you guys may have. Oh, yes, now I remember. Sorry, there was a mental bug. One of the things that happen with linear algebra, especially with matrix multiplication, is they are very well suited to also be done on GPUs, on graphic processing units. And We're going to maybe see a little bit of CPU programming at the end of the course, one lecture perhaps or so, just to get you an idea. So there are advantages and disadvantages, right? It's like everything in programming. There is no free lunch here. But one of the things that one needs to contemplate when thinking about using CPUs is the difference in the architecture, in the hardware itself. One of the limiting factors usually is memory. Because memories are one of the limiting factors, usually the bottleneck where things get slow in the CPU is the communication between information or the communication between the CPU and the CPU. So passing the information to perform the operation. So performing operations is very fast on the CPU. They are aimed for that, but the bandwidth of communicating that can be the constraint element there. Having said that, there are specialized libraries, like for instance, there are a lot of libraries that are developed in CUDA, and you can try to optimize some of the linear algebra operations. I think there is a linal CUDA library that is very well suited for performing a lot of linear algebra on the GPU. I didn't include this one here because, as I say, we are talking more about programming traditional CPU processes, but we may talk about that at the end of the course. Yeah, so PHY can do way more than that, I would say. Let me go back at the beginning where I talk about PHY. So PHY can do that, but actually what it shines is for partial differential equation solvers and iterative linear solvers. So I wouldn't say that's the same as BLAS and LAPAC, but it does something different. Having said that, it may have some basic routines, but they wouldn't be comparable to all the other routines that BLAS and LAPAC offers. I think Linux may have some of the functionalities that BLAS and LAPAC offer. Maybe between PHY and Linux, you may cover much of the ground that BLAS and LAPAC uses. Does, sorry. Okay. Again, it's a quite fascinating topic, I think, especially because we are able to translate into simple mathematical operations, many complex implementations. But even when you do that, you will reach the point where the stagnation point, though, is the technicalities in the details, because not the implementation itself, because it can be done, but because of the performance issues. So sometimes is the really struggling point there. Okay. Yeah, and as Francis mentioned, PHY uses BLAS and LAPAC. Many of the things use BLAS and LAPAC. So even when you may not, so this is something that usually happens as well, right? Especially with people trying to go all C++. Even when BLAS and LAPAC may sound and feel, what's the right word to describe this, all stylish or outdated, they are still being kind of the main reference for more grown-up libraries. So people keeps using them. They keep, they are up to date in all what is performance issues. I think, I can't remember, Francis, I think we were together in a conference a couple of years ago where there was someone trying. So one of the paradigms that are switching nowadays in high performance computing is, until some point, the really constraint was performing more computations. Nowadays, we have hardware that is able to take as much computations as you want to do and perform the computation. And what is starving for is data, the flow of data being passed in such a way that is agile and keeps the CPU busy. And the same in particular happens for GPUs. So one of the shift in paradigms that were happening is, okay, what's about having data distribute instead of computation distribute? So can we distribute the data and have the implementation done somewhere else and then recombine that? So that shift in paradigm will change the basics of how these libraries work. But as I say, we were a couple of years, maybe 4 or 5 years ago in a conference, and if I remember properly, there were some ideas to try to implement that, but I haven't seen anything on that regards. Maybe Rancis remembers better or have heard anything about that. But as far as I know, I think that's one of the standards in the field.
Yeah, it's true. Actually, a lot of the commercial implementations or better implementations like OpenBLAS get their optimization by being clever about how they access data. And for a lot of cases, you might need to know the intricate details of the memory subsystem of your chip. But there are ways to make it more generic, but they are even more complex. So another reason why you don't want to just write a triple loop, because you're not going to take advantage of any of that. So, yeah.
That's the secret sauce that they don't need. But yeah, so that's something to keep an eye on, right? As hardware develops and new approaches, some things may change. As I can say right now, these are really good standards to use. And of course, as I also mentioned, it depends a lot on which systems you're running, right? So on Signer, for instance, we have Niagara, which is our main cluster, which is CPU driven, it's all CPU based. But if you are using MIST, which is a smaller cluster, but it's all composed by GPUs. So all the nodes has 4 GPUs each. So you definitely won't be running the same type of code in terms of getting the best performance as you will be doing on the Niagara cluster if you're using the MIST cluster. So this is one of the first lessons that one learns when you want to go into high performance computing, right? Is you need to understand and be familiar with the hardware also, just to get the best code or the best performance in your code, right? You just don't program in a generic manner. You could do it if you want to use OpenCL, but we won't teach you that. I won't teach you that, maybe Rancis, but not me. All right. Okay. So I think that's it for today. Again, we will see you guys tomorrow during office hours. And if you guys have any questions, again, feel free to post in the forum or by email. I think Shisha, you did have a question about your the code that you got for the assignment. So let me just stop the recording and we can talk about that. Okay.
Okay. Thank you.